So firstly, a quick reminder that last week we discussed how the interior of stars can microscopically be well described by the ideal gas equation of state, in which the pressure of the gas is equal to 2/3 times the energy density of the gas, the energy per unit volume. Or to write it another way round, the energy density of a gas is 3/2 the pressure of the gas. And you can calculate the total thermal energy of the star, let's call it big U thermal, just by adding up the thermal energy in every microscopic part of the star. In other words, integrating U thermal with respect to volume. Last week we also derived the total gravitational potential energy of the star. We saw that this was just the integral of 4 pi r squared dr times the mass inside radius of r times the density inside radius of r divided by r. And this just said that the gravitational potential energy caused by a spherical shell of matter of thickness dr and surface area 4 pi r squared, it has a mass 4 pi r squared times dr times its density rho of r. So this is the mass of the spherical shell, and therefore the gravitational potential energy of that spherical shell by Newton's law of gravity is minus, and I've left off the big G, Newton's constant, is minus big G times dm times the mass of the star that's already there underneath it divided by r. So that's Newton's law of gravity, and then the total gravitational energy you get by adding up all the spherical shells that make up the star, in other words, integrating this. And we showed that if you approximate the density to be a constant that takes the average value of the density, then to an order of magnitude, this is minus 3/5 gm over r. Okay, now I'm not going to derive it, but there is, not in this lecture at least, I'm going to derive it in some notes that I'm going to put up this week. But there is a very nice theorem that relates these two forms of energy that the star has. These are the two forms of energy that a star has. It has thermal energy and it has gravitational potential energy. And there is a theorem called the Virial theorem, and that simply says, and as I said, I'll derive this in the notes, it's also derived in the textbook, that so long as we can well describe the interior with an ideal gas, then twice the total thermal energy of the star plus the gravitational potential energy of the star is equal to 0. Or in other words, the gravitational potential energy is minus twice the thermal energy, or the thermal energy is minus 1/2 the gravitational potential energy. You can write it in any of these three ways. And this is an extremely useful theorem. It tells us that the fundamental assumption of this is that the star is in hydrostatic equilibrium. And as we saw last week, what that means is that the force of gravity is not independent of the pressure inside the star. The pressure force must balance the gravity force exactly. And so it's not surprising that turning this into an energy relation, that the total thermal energy of the star, this is the energy essentially that causes the pressure force, and the gravitational potential energy associated with the gravitational force are also related. Right? So a way of thinking of the Virial theorem is that this is the energy version of writing Newton's first law, that the gravitational force must be equal to minus the pressure force. In other words, the hydrostatic equilibrium relation. Now this is very useful, and I'll give you a couple of examples of why it is useful. Firstly, we can write down the total energy of the star, which is just the sum of the thermal energy and the gravitational potential energy. And if we use the fact that the thermal energy is minus 1/2 the gravitational potential energy, and substitute this in here, we find the total energy is 1/2 UG. Or we could substitute in minus 2 U thermal for U gravitational, and we'll find that the total energy is also equal to minus the thermal energy of the star. Okay, the thermal energy of the star is always positive. It comes from the kinetic energy of the random motion of the ions and atoms that make up the star. So this tells us that the total energy is negative. And any system that has a total energy that is negative is a bound system. In other words, the forces that act on the system cause it to be held together. Right? It isn't. The constituent parts of the system are not free to fly off to infinity. And in this case, it is bound by the force of gravity. So we say that it is a star is a gravitationally bound object. So that's useful information and comforting. A second thing that we can use the Virial theorem to do is to analyze the stability of a star. And I'm going to do one analysis, and I'm going to ask you to do another similar analysis in the homework. Let's suppose, for example, that some event, something happens in the star that causes it to catastrophically lose pressure. So the star loses a significant amount of its internal pressure. We can use the Virial theorem to analyze how the star will respond to the sudden loss of pressure. Well, if the pressure force decreases, then in the balance of forces, gravity will win and the star will start contracting. And if the star starts contracting, then the gravitational potential energy will decrease. It will become more negative. Okay. Again, think if I drop a pen, in other words, if the pen Earth system contracts by the pen and the Earth getting closer together, the gravitational potential energy of the pen Earth system decreases. If I pick the pen up, the gravitational potential energy increases. But if the gravitational potential energy goes down, then the thermal energy of the star, the total thermal energy of the star, which is minus half the gravitational potential energy, that has to increase. Right? If this quantity goes down, then this is minus this, so that has to go up. So one consequence is that the thermal energy increases. And if the thermal energy increases, then the pressure, which is related to the thermal energy, increases. And so the net result of losing pressure is that the pressure increases inside the star. And therefore the star can stabilize. So there is in a sense, a positive feedback loop. That means that the star is stable to losses of pressure. You lose pressure, star contracts, thermal energy increases, which means it heats up, and therefore the pressure increases and restabilizes the star. How long does it take the star to restabilize? Well, that's given by the dynamical time scale that we estimated last week. For the Sun, we found that to an order of magnitude, it's about an hour. So if the Sun suddenly loses a whole load of pressure somehow in its interior, it will take an hour for it to restabilize. That's the order of magnitude for the response time. Okay, now, not that most of the interior of the Sun can be well described by the ideal gas equation of state, but there are situations in which that is not the case. There will be stars where that is not the case. And we saw last week that a more general relation between the pressure and the energy density is that the pressure is equal to this constant, the adiabatic index, minus 1 times the thermal energy density. And gamma is 5/3 for an ideal gas. Plugging this into the virial theorem, or going through the virial theorem with this equation of state, we find that more generally the virial theorem says that 3 times gamma minus 1 times the total thermal energy of the star plus the gravitational potential energy of the star is equal to 0, and that the total energy of the star is minus 3 gamma minus 4 times the thermal energy of the star. So let's examine an application of this. Now, it turns out that in very massive stars, a lot of the pressure is generated by the light radiation or the electromagnetic radiation released by the nuclear reactions going on in the core. This radiation is in thermal equilibrium, so it's a black body spectrum, but you can treat the radiation as a gas. It's a gas of photons, photons being the particles that comprise light. And it turns out that those photons exert a pressure. We call this radiation pressure. And the gas of photons obeys an equation of state given by this relation here with the adiabatic index equal to 4/3. Now this is interesting because if you plug 4/3 into the total energy of the star, 3 times 4/3 minus 4 is 0. So the total energy of a star that is supported mainly by radiation pressure is approximately 0. Therefore, it is teetering on the cusp of being unbound. If the total energy of the star becomes positive, then the star is unbound and the pressure inside will dominate the gravitational force and push matter out into space. So very massive stars tend to go unstable at certain times and eject matter from their atmosphere into space. And that is a consequence of the thermodynamics of the photon gas that is responsible for a large part of their pressure. It's useful to look at the temperature dependence of the photon gas versus the ideal gas. For an ideal gas, we saw last week that the ideal gas equation of state tells us that the thermal energy density is rho over mass of hydrogen times m molecular mass times 3/2 Boltzmann's constant times temperature. So as far as temperature is concerned, thermal energy density of an ideal gas is proportional to temperature, whereas the thermal energy density of a photon gas is equal to a constant, A, times temperature to the 4th power. This is nothing other than the Stefan-Boltzmann law. This is the temperature dependence of black body radiation. And that is what describes the photon gas in thermodynamic equilibrium. So a black body photon gas has an energy density proportional to temperature to the 4th power. So this is a much higher power than the dependence of the ideal gas energy density. And so one consequence is that at low temperatures, the thermal energy that comes from the matter particles will win and will dominate the energy density and therefore the thermal energy of the star, whereas at very high temperatures, the thermal energy of the photons comes to dominate. We can qualitatively sketch these relations. So if we sketch the thermal energy density versus temperature, then for an ideal gas, the relation is linear. And for a photon gas, it goes as T to the 4th power. So that is something that looks like that. So at low temperatures, say we're down around the, in quotes, low temperatures, only 10 million degrees at the center of the sun, then the ideal gas supports most of, or is responsible for most of the thermal energy density of the star. Whereas if you go to higher densities, around 10 to the 9 Kelvin, which can be reached in the interior of very massive stars, remember our sun is really a very small star in the scheme of things, then the energy density due to the photon gas wins, and the pressure that supports the star comes mostly from the radiation.